a research team led by Dr. John Morton from Oxford University and Professor Kohei Ito from Keio University, with collaboration from Simon Fraser University and others, has succeeded in the generation and detection of entanglement in silicon. The weird quantum phenomenon of entanglement has challenged our intuitions since the idea was born over 100 years ago, but it is only recently that entanglement has become recognized as the key ingredient behind revolutionary quantum technologies such as quantum computers, which could perform calculations that are impossible using computers today.
The idea of superposition describes the phenomenon where something can exist in two different states at the same time. This may seem like a rather odd idea, and indeed it challenged the pioneers of quantum mechanics because it goes against our experiences of everyday life. For example, you might imagine me sitting here, or you might imagine me sitting over here. But you would never imagine me sitting in both places at the same time. But quantum mechanics allows exactly this through the principle of superposition. It says that atoms, electrons, and molecules can be in two different states at the same time, and this is a very powerful idea for quantum technologies. A related idea is called entanglement, which requires two quantum objects. Now they can interact in such a way to become entangled so that it's impossible to describe one without also describing the other. And they can be separated, sent to the other ends of the universe, but then a measurement on one affects the result of a measurement on the other.
In order to understand entanglement, one first needs to appreciate a quantum mechanical property called superposition. Suppose you have a friend who has one bottle of red wine and one of white, and who has given one of them to you as a gift in a box. Following classical mechanics, the wine you receive must either be red or white. However, quantum mechanics allows the box to contain a bottle of red wine and white wine simultaneously, in what is called a superposition state. Once the box is opened, however, you will find only one bottle, having determined whether it is red or white, and collapsing the superposition into a classical state. Now suppose you know your friend also sent the other bottle in a box somewhere else, perhaps to a relative on the other side of the world. Your box of wine can be said to be entangled with the other. The instant you open your box and determine whether your wine is red or white, you also collapse the state of the other box of wine as you have determined its color as well. So we see that quantum entanglement describes a correlated state, transcending time and space, that can't be explained with classical mechanics. When one of two entangled quantum objects is measured, so taking on a classical state, the other half of the entangled pair instantaneously takes on a classical state, regardless of how separated they may be. Entanglement has been generated and detected in the past using photons in vacuum and superconducting circuits. However, realization of entanglement in the industrially important and technologically advanced semiconductor material silicon has been eagerly waited. To achieve this goal, N-type silicon is produced by adding phosphorus impurities to silicon. Phosphorus atoms in silicon at low temperatures, less than 20 degrees absolute, capture an electron and behave like hydrogen atoms. Here, the presence of background can be ignored and regarded as vacuum. Therefore, the situation of hydrogen atoms placed in vacuum can be realized by placing phosphorus in silicon solid. The nuclear spin of a phosphorus atom is considered as one quantum bit, and the captured electron's spin is another quantum bit, and entanglement is created between the two quantum bits. However, until now, random distribution of three stable isotopes of silicon disturbed the uniformity in space, and a truly vacuum-like environment was difficult to achieve. But a group led by Professor Kohei Ito at Keio University and Professor Mike Thewalt at Simon Fraser University has succeeded in making a truly vacuum-like environment within silicon by removing this non-uniformity by ensuring that all atoms in the silicon are the stable isotope silicon-28.
We have been working on so-called isotope engineering of semiconductors in the past 15 years. This machine, for example, allows us to stack atom by atom different isotopes of silicon, 28, 29, and 30. And basically, we can stack them any way we want. In this particular research, we wanted to make vacuum in solid. Vacuum in solid. This may sound strange to you, but this basically means that we want to remove inhomogeneity or non-uniformity due to mass and magnetic fluctuations as much as possible. And to do so, we just needed to make highly pure, highly perfect silicon with only one kind of isotope, namely 28 silicon.
Building on these results, Stephanie Simmons, Richard Brown and Dr. John Morton at Oxford University use special magnetic resonance equipment which can operate at less than 3 degrees absolute with a magnetic field of 3.4 Tesla to successfully obtain high polarization of nuclear spin and electron spin in phosphorus atoms. This led to the successful creation and detection of entanglement.
So in these experiments we use phosphorus-doped silicon. Now in its bulk form, this really forms the basis of modern-day computing. But what we can actually do now is store information in single dopant atoms, but it also has the advantage that it can be integrated into existing technologies.
So when we store information in these individual atoms, the reason we chose this material is also because it can store that information for a very, very long time. And another very important characteristic is that we're able to manipulate the quantum information with a very, very high fidelity. So with these two characteristics, we're able to perform these very complicated and long quantum sequences.
The results of this research will be published in the February 2011 issue of Nature.